Section 4 of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Blaine Aidan McCoy, Riverside, California, January 2019. The neutron, nuclear spin. What Rutherford did not and could not take into account were the consequences of a completely new type of nuclear bombardment involving a type of particle unknown in the 1920s, though Rutherford speculated about the possibility of its existence. The beginnings of the new path came about through the reluctant realization that there was a flaw in the apparently firmly grounded proton-electron picture of nuclear structure. The flaw involved the nuclear spin. In 1924, the Austrian physicist Wolfgang Pauli, 1900 to 1958, worked out a theory that treated protons and electrons as though they were spinning on their axes. This spin could be in either direction, or, as we would say in earthly terms, from west to east or from east to west. Quantum theory has shown that a natural unit exists for what is called the angular momentum of this spin. Measured in terms of this natural unit of spin, the proton and electron have spin 1/2. If the particle spun in one direction, it was plus 1/2. If in the other, it was minus 1/2. When subatomic particles came together to form an atomic nucleus, each kept its original spin, and the nuclear spin was then equal to the total angular momentum of the individual particles that made it up. For instance, suppose the helium nucleus is made up of 4 protons and 2 electrons, as was thought in the 1920s. Of the 4 protons, suppose that 2 had a spin of plus 1/2 and 2 of minus 1/2. Suppose also that of the 2 electrons, 1 had a spin of plus 1/2 and 1 of minus 1/2. All the spins would cancel each other. The total angular momentum would be 0. Of course, it is also possible that all 6 particles were spinning in the same direction, all plus 1/2 or all minus 1/2. In that case, the nuclear spin would be 3, either in one direction or the other. If 5 particles were spinning in one direction and 1 in the other, then the total spin would be 2 in one direction or the other. In short, if you have an even number of particles in a nucleus, each with a spin of plus 1/2 or minus 1/2, then the total spin is either 0 or a whole number, no matter what combination of positive and negative spins you choose. The total spin is always written as a positive number. On the other hand, suppose you have lithium-7, which was thought to be made up of 7 protons and 4 electrons. If the 7 protons were all plus 1/2 and the 4 electrons were all minus 1/2 in their spins, the nuclear spin would be 7/2 minus 4/2 equals 3/2. If you have an odd number of particles in the nucleus, you will find that any combination of positive and negative spins will never give you either 0 or a whole number as a sum. The sum will always include a fraction. Consequently, if one measures the spin of a particular atomic nucleus, one can tell at once whether that nucleus contains an even number of particles or an odd number. This quickly raised a problem. The nuclear spin of the common isotope nitrogen-14 was measured accurately over and over again and turned out to be 1. There seemed no doubt about that, and it could therefore be concluded that there were an even number of particles in the nitrogen-14 nucleus. And yet, by the proton-electron theory of nuclear structure, the nitrogen-14 nucleus with a mass number of 14 and an atomic number of 7, had to be made up of 14 protons and 7 electrons for a total of 21 particles altogether, an odd number. The nuclear spin of nitrogen-14 indicated even number, and the proton-electron theory indicated odd number. One or the other had to be wrong, but which? The nuclear spin was a matter of actual measurement which could be repeated over and over, and on which all agreed. The proton-electron theory was only a theory. It was therefore the latter that was questioned. What was to be done? Suppose it is wrong to count protons and electrons inside the nucleus as separate particles. Was it possible that an electron and a proton, forced into the close confinement of the atomic nucleus, might, by the force of mutual attraction, become so intimately connected as to count as a single particle? One of the first to suggest this, as far back as 1920, was Rutherford. Such a proton-electron combination would be electrically neutral, and in 1921 the American chemist William Draper Harkins, 1873 to 1951, used the term neutron as a name for it. If we look at the nitrogen-14 nucleus in this way, then it is made up not of 14 protons and 7 electrons, but of 7 protons and 7 proton-electron combinations. Instead of a total of 21 particles, there would be a total of 14. Instead of an odd number, there would be an even number. The structure would now account for the nuclear spin. But could such a revised theory of nuclear structure be made to seem plausible? The proton-electron theory seemed to make sense because both protons and electrons were known to exist separately and could be detected. If an intimate proton-electron combination could also exist, ought it not exist or be made to exist outside the nucleus, and ought it not be detected as an isolated particle? Discovery of the neutron. Throughout the 1920s, scientists searched for the neutron, but without success. One of the troubles was that the particle was electrically neutral. Subatomic particles could be detected in a variety of ways, but every single way, right down to the present time, makes use of their electric charge. The electric charge of a speeding subatomic particle either repels electrons or attracts them. In either case, electrons are knocked off atoms that are encountered by the speeding subatomic particle. The atoms with electrons knocked off are now positively charged ions. Droplets of water vapor can form about these ions, or a bubble of gas can form, or a spark of light can be seen. The droplets, the bubbles, and the light can all be detected one way or another, and the path of the subatomic particle could be followed by the trail of ions it left behind. Gamma rays, though they carry no charge, are a waveform capable of ionizing atoms. All the particles and rays that can leave a detectable track of ions behind are called ionizing radiation, and these are easy to detect. The hypothetical proton-electron combination, however, which was neither a wave form nor a charged particle, was not expected to be able to ionize atoms. It would wander among the atoms without either attracting or repelling electrons, and would therefore leave the atomic structure intact. Its pathway could not be followed. In short, then, the neutron was, so to speak, invisible, and the search for it seemed a lost cause. And until it was found, the proton-electron theory of nuclear structure, whatever its obvious deficiencies with respect to nuclear spin, remained the only one to work with. Then came 1930. The German physicist Walther Wilhelm Georg Botha, 1891 to 1957, and a co-worker, H. Becker, were bombarding the light metal beryllium with alpha particles. Ordinarily, they might expect protons to be knocked out of it, but in this case no protons appeared. They detected some sort of radiation because something was creating certain effects while the alpha particles were bombarding the beryllium, but not after the bombardment ceased. To try to determine something about the properties of this radiation, Botha and Becher tried putting objects in the way of the radiation. They found the radiation to be remarkably penetrating. It even passed through several centimeters of lead. The only form of radiation that was known at that time to come out of bombarded matter with the capacity of penetrating a thick layer of lead was gamma rays. Botha and Becher therefore decided they had produced gamma rays and reported this. In 1932, the Joliot-Curies repeated the Botha-Becher work and got the same results. However, among the objects they placed in the path of the new radiation, they included paraffin, which is made up of the light atoms of carbon and hydrogen. To their surprise, protons were knocked out of the paraffin. Gamma rays had never been observed to do this, but the Joliot-Curies could not think what else the radiation might be. They simply reported that they had discovered gamma rays to be capable of a new kind of action. Not so the English physicist James Chadwick, born 1891. In that same year he maintained that a gamma ray which possessed no mass simply lacked the momentum to hurl a proton out of its place in the atom. Even an electron was too light to do so. It would be like trying to knock a baseball off the ground and into the air by hitting it with a ping-pong ball. Any radiation capable of knocking a proton out of an atom had to consist of particles that were themselves pretty massive. And if one argued like that, then it seemed that the radiation first observed by Botha and Becher had to be the long-sought-for proton-electron combination. Chadwick used Harkin's term neutron for it and made it official. He gets the credit for discovery of the neutron. Chadwick managed to work out the mass of the neutron from his experiments, and by 1934 it was quite clear that the neutron was more massive than the proton. The best modern data have the mass of the proton set at 1.007825, and that of the neutron just a trifle greater at 1.008665. The fact that the neutron was just about as massive as the proton was to be expected if the neutron were a proton-electron combination. It was also not surprising that the isolated neutron eventually breaks up, giving up an electron and becoming a proton. Out of any number of neutrons, half have turned into protons in about 12 minutes. Nevertheless, although in some ways we can explain the neutron by speaking of it as though it were a proton-electron combination, it really is not. A neutron has a spin of 1/2, while a proton-electron combination would have a spin of either 0 or 1. The neutron therefore must be treated as a single uncharged particle. The proton-neutron theory. As soon as the neutron was discovered, the German physicist Werner Karl Heisenberg, born 1901, revived the notion that the nucleus must be made up of protons and neutrons rather than protons and electrons. It was very easy to switch from the latter theory to the former if one simply remembered to pair the electrons thought to be in the nucleus with protons and give the name neutrons to these combinations. Thus, the helium-4 nucleus, rather than being made up of 4 protons and 2 electrons, was made up of 2 protons and 2 proton-electron combinations, or 2 protons and 2 neutrons. In the same way, the oxygen-16 nucleus, instead of being made up of 16 protons and 8 electrons, would be made up of 8 protons and 8 neutrons. The proton-neutron theory would account for mass numbers and atomic numbers perfectly well. If a nucleus was made up of X protons and Y neutrons, then the atomic number was equal to X and the mass number to X plus Y. It is now possible to define the mass number of a nucleus in modern terms. It is the number of protons plus neutrons in the nucleus. The proton-neutron theory of nuclear structure could account for isotopes perfectly well, too. Consider the three oxygen isotopes, oxygen-16, oxygen-17, and oxygen-18. The first would have a nucleus made up of 8 protons and 8 neutrons. The second, one of 8 protons and 9 neutrons. And the third, one of 8 protons and 10 neutrons. In each case, the atomic number is 8. The mass numbers, however, would be 16, 17, and 18, respectively. In the same way, uranium-238 would have a nucleus built of 92 protons and 146 neutrons, while uranium-235 would have one of 92 protons and 143 neutrons. By the new theory, can we suppose that it is neutrons rather than electrons that somehow hold the protons together against their mutual repulsion, and that more and more neutrons are required to do this as the nucleus grows more massive? At first, the number of neutrons required is roughly equal to the number of protons. The helium-4 nucleus contains 2 protons and 2 neutrons. The carbon-12 nucleus contains 6 protons and 6 neutrons. The oxygen-16 nucleus contains 8 protons and 8 neutrons, and so on. For more complicated nuclei, additional neutrons are needed. In vanadium-51, the nucleus contains 23 protons and 28 neutrons, 5 more than an equal amount. In bismuth-209, it is 83 protons and 126 neutrons, 43 more than an equal amount. For still more massive nuclei containing a larger number of protons, no amount of neutrons is sufficient to keep the assembly stable. The more massive nuclei are all radioactive. The manner of radioactive breakdown fits the theory too. Suppose a nucleus gives off an alpha particle. The alpha particle is a helium nucleus made up of 2 protons and 2 neutrons. If a nucleus loses an alpha particle, its mass number should decline by 4, and its atomic number by 2, and that is what happens. Suppose a nucleus gives off a beta particle. For a moment that might seem puzzling. If the nucleus contains only protons and neutrons and no electrons, where does the beta particle come from? Suppose we consider the neutrons as proton-electron combinations. Within many nuclei, the neutrons are quite stable and do not break up as they do in isolation. In the case of certain nuclei, however, they do break up. Thus, the thorium-234 nucleus is made up of 90 protons and 144 neutrons. One of these neutrons might be viewed as breaking up to liberate an electron and leaving behind an unbound proton. If a beta particle leaves, then, the number of neutrons decreases by 1 and the number of protons increases by 1. The thorium-234 nucleus, 90 protons, 144 neutrons, becomes a proactinium-234 nucleus, 91 protons, 143 neutrons. In short, the proton-neutron theory of nuclear structure could explain all the observed facts just as well as the proton-electron theory, and could explain the nuclear spins which the proton-electron theory could not. What's more, the isolated neutron had been discovered. The proton-neutron theory was therefore accepted and remains accepted to this day. The nuclear interaction. In one place, and only one, did the proton-neutron theory seem a little weaker than the proton-electron theory. The electrons in the nucleus were thought to act as a kind of glue holding together the protons. But the electrons were gone. There were no negative charges at all inside the nucleus, only the positive charges of the proton, plus the uncharged neutron. As many as 83 positive charges were to be found in the bismuth 209 nucleus, squeezed together and yet not breaking apart. In the absence of electrons, what kept the protons clinging together? Was it possible that the electrical repulsion between two protons is replaced by an attraction if those protons were pushed together closely enough? Can there be both an attraction and a repulsion, with the former the more important at very short range? If this were so, that hypothetical attraction would have to have two properties. First, it would have to be extremely strong, strong enough to overcome the repulsion of two positive charges at very close quarters. Secondly, it would have to be short range, for no attractive force between protons of any kind was ever detected outside the nucleus. In addition, this short-range attraction would have to involve the neutron. The hydrogen-1 nucleus was made up of a single proton, but all nuclei containing more than one proton had to contain neutrons also to be stable, and only certain numbers of neutrons. Until the discovery of the neutron, only two kinds of forces or interactions were known in the universe. These were the gravitational interaction and the electromagnetic interaction. The electromagnetic interaction was much the stronger of the two, trillions and trillions and trillions of times as strong as the gravitational attraction. The electromagnetic attraction, however, includes both attraction between opposite electric charges or between opposite magnetic poles, and repulsion between like electric charges or magnetic poles. In ordinary bodies, the attractions and repulsions usually cancel each other entirely or nearly entirely, leaving very little of one or the other to be detected as surplus. The gravitational interaction, however, includes only attraction, and this increases with mass. By the time you have gigantic masses, such as the Earth or the Sun, the gravitational interaction between them and other bodies is also gigantic. Both the gravitational and electromagnetic interactions are long-range. The intensity of each interaction declines with distance, but only as the square of the distance. If the distance between Earth and Sun were doubled, the gravitational interaction would still be 1/4 what it is now. If the distance were increased 10 times, the interaction would still be 1/10 times 10, or 1/100th what it is now. It is for this reason that gravitational and electromagnetic interactions can make themselves felt over millions of miles of space. But now, with the acceptance of the proton-neutron theory of nuclear structure, physicists began to suspect the existence of a third interaction, a nuclear interaction, much stronger than the electromagnetic interaction, perhaps 130 times as strong. Furthermore, the nuclear interaction had to decline very rapidly with distance, much more rapidly than the electromagnetic interaction did. In that case, protons in virtual contact, as within the nucleus, would attract each other, but if the distance between them was increased sufficiently to place one outside the nucleus, the nuclear interaction would decrease in intensity to less than the electromagnetic repulsion. The proton would now be repelled by the positive charge of the nucleus and would go flying away. That is why atomic nuclei have to be so small. It is only when they are so tiny that the nuclear interaction can hold them together. In 1932, Heisenberg tried to work out how these interactions might come into being. He suggested that attractions and repulsions were the result of particles being constantly and rapidly exchanged by the bodies experiencing the attractions and repulsions. Under some conditions, these exchange particles, moving back and forth very rapidly between two bodies, might force those bodies apart. Under other conditions, they might pull those bodies together. In the case of the electromagnetic interaction, the exchange particles seemed to be photons, wave packets that made up gamma rays, X-rays, or even ordinary light, all of which are examples of electromagnetic radiation. The gravitational interaction would be the result of exchange particles called gravitons. In 1969, there were reports that gravitons had actually been detected. Both the photon and the graviton have zero mass, and there is a connection between that and the fact that electromagnetic interaction and gravitational interaction decline only slowly with distance. For a nuclear interaction, which declines very rapidly with distance, the exchange particle, if any, would have to have mass. In 1935, the Japanese physicist Hideki Yukawa, born 1907, worked out in considerable detail the theory of such exchange particles in order to decide what kind of properties the one involved in the nuclear interaction would have. He decided it ought to have a mass about 250 times that of an electron, which would make it about 1/7 as massive as a proton. Since this mass is intermediate between that of an electron and proton, such particles eventually came to be called mesons, from a Greek word meaning intermediate. Once Yukawa published his theory, the search was on for the hypothetical mesons. Ideally, if they existed within the nucleus, shooting back and forth between protons and neutrons, there ought to be some way of knocking them out of the nucleus and studying them in isolation. Unfortunately, the bombarding particles at the disposal of physicists in the 1930s possessed far too little energy to knock mesons out of nuclei, assuming they were there in the first place. There was one way out. In 1911, the Austrian physicist Victor Francis Hess, 1883 to 1964, had discovered that Earth was bombarded from every side by cosmic rays. These consisted of speeding atomic nuclei, cosmic particles, of enormous energies, in some cases billions of times as intense as any energies available through particles produced by mankind. If a cosmic particle of sufficient energy struck an atomic nucleus in the atmosphere, it might knock mesons out of it. In 1936, the American physicists Carl David Anderson, born 1905, and Seth Henry Nettermeyer, born 1907, studying the results of cosmic particle bombardment of matter, detected the existence of particles of intermediate mass. This particle turned out to be lighter than Yukawa had predicted. It was only about 207 times as massive as an electron. Much worse, it lacked other properties that Yukawa had predicted. It did not interact with the nucleus in the manner expected. In 1947, however, the English physicist Cecil Frank Powell, 1903 to 1969, and his co-workers, also studying cosmic particle bombardment, located another intermediate-sized body, which had the right mass and all the other appropriate properties to fit Yukawa's theories. Anderson's particle was called a mu meson, soon abbreviated to muon. Powell's particle was called a pi meson, soon abbreviated to pion. With the discovery of the pion, Yukawa's theory was nailed down, and any lingering doubt as to the validity of the proton-neutron theory vanished. Actually, It turns out that there are two forces. The one with the pion as exchange particle is the strong nuclear interaction. Another, involved in beta particle emission, for instance, is a weak interaction, much weaker than the electromagnetic, but stronger than the gravitational. The working out of the details of the strong nuclear interaction explains further the vast energies to be found resulting from nuclear reactions. Ordinary chemical reactions, with the electron shifts that accompany them, involve the electromagnetic interaction only. Nuclear energy, with the shifts of the particles inside the nucleus, involves the much stronger nuclear interaction. Neutron bombardment. As soon as neutrons were discovered, it seemed to physicists that they had another possible bombarding particle of extraordinary properties. Since the neutron lacked any electric charge, it could not be repelled by either electrons on the outside of the atoms or by the nuclei at the center. The neutron was completely indifferent to the electromagnetic attraction, and it just moved along in a straight line. If it happened to be headed toward a nucleus, it would strike it, no matter how heavy a charge that nucleus might have, and very often it would, as a result, induce a nuclear reaction where a proton would not have been able to. To be sure, it seemed just at first that there was a disadvantage to the neutron's lack of charge. It could not be accelerated directly by any device, since that always depended on electromagnetic interaction, to which the neutron was impervious. There was one way of getting around this, and this was explained in 1935 by the American physicist J. Robert Oppenheimer, 1904 to 1967, and by his student Melba Phillips. Use is made here of the nucleus of the hydrogen-2 deuterium nucleus. That nucleus, often called a deuteron, is made up of one proton plus one neutron, and has a mass number of 2 and an atomic number of 1. Since it has a unit positive charge, it can be accelerated just as an isolated proton can be. Suppose, then, that a deuteron is accelerated to a high energy and is aimed right at a positively charged nucleus. That nucleus repels the deuteron, and it particularly repels the proton part. The nuclear interaction that holds together a single proton and a single neutron is comparatively weak as nuclear interactions go, and the repulsion of the nucleus that the deuteron is approaching may force the proton out of the deuteron altogether. The proton veers off, but the neutron, unaffected, keeps right on going, and, with all the energy it had gained as part of the deuteron acceleration, smashes into the nucleus. Within a few months of their discovery, energetic neutrons were being used to bring about nuclear reactions. Actually, though, physicists didn't have to worry about making neutrons energetic. This was a hangover from their work with positively charged particles, such as protons and alpha particles. These charged particles had to be energetic to overcome the repulsion of the nucleus and to smash into it with enough force to break it up. Neutrons, however, didn't have to overcome any repulsion. No matter how little energy they had, if they were correctly aimed, and some always were through sheer chance, they would approach and strike the nucleus. In fact, the more slowly they traveled, the longer they would stay in the vicinity of a nucleus, and the more likely they were to be captured by some nearby nucleus through the attraction of the nuclear interaction. The influence of the nucleus in capturing the neutron was greater the slower the neutron, so that it was almost as though the nucleus were larger and easier to hit for a slow neutron than a fast one. Eventually, physicists began to speak of nuclear cross-sections, and to say that particular nuclei had a cross-section of such and such a size, for this bombarding particle or that. The effectiveness of slow neutrons was discovered in 1934 by the Italian-American physicist Enrico Fermi, 1901 to 1954. Of course, there was the difficulty that neutrons couldn't be slowed down once they were formed, and as formed they generally had too much energy, according to the new way of looking at things. At least they couldn't be slowed down by electromagnetic methods, but there were other ways. A neutron didn't always enter a nucleus that it encountered. Sometimes, if it struck the nucleus a hard, glancing blow, it bounced off. If the nucleus struck by the neutron is many times as massive as the neutron bounced off with all its speed practically intact. On the other hand, if the neutron hits a nucleus not very much more massive than itself, the nucleus rebounds and absorbs some of the energy, so that the neutron bounces away with less energy than it had. If the neutron rebounds from a number of comparatively light nuclei, it eventually loses virtually all its energy, and finally moves about quite slowly, possessing no more energy than the atoms that surround it. You can encounter this situation in ordinary life in the case of billiard balls. A billiard ball colliding with a cannonball will just bounce, moving just as rapidly afterward as before, though in a different direction. If a billiard ball strikes another billiard ball, it will set the target ball moving and bounce off itself with less speed. The energy of the molecules in the atmosphere depends on temperature. Neutrons that match that energy and have the ordinary quantity to be expected at room temperature are called thermal, from a Greek word meaning heat, neutrons. The comparatively light nuclei against which the neutrons bounce and slow down are moderators, because they moderate the neutron's energy. Fermi and his co-workers were the first to moderate neutrons, produce thermal neutrons, and use them in 1935 to bombard nuclei. He quickly noted how large nuclear cross-sections became when thermal neutrons were the bombarding particles. It might seem that hope could now rise in connection with the practical use of energy derived from nuclear reactions. Neutrons could bring about nuclear reactions even when they themselves possessed very little energy, so output might conceivably be more than input for each neutron that struck. Furthermore, because of the large cross-sections involved, thermal neutrons missed far less frequently than high-energy charged particles did. But there was a catch. Before neutrons could be used, however low energy and however sure to hit, they had to be produced. And in order to produce neutrons, they had to be knocked out of nuclei by bombardment with high-energy protons or some other method. The energy formed by the neutrons was at first never more than the tiniest fraction of the energies that went into forming the neutrons in the first place. It was as though you could indeed light a candle with a single match, but you still had to look through 300,000 useless pieces of wood before you found a match. The candle would still be impractical. Even with the existence of neutron bombardment involving low energy and high cross-section, Rutherford could, with justice, feel right down to the time of his death that nuclear energy would never be made available for practical use. And yet, among the experiments that Fermi was trying in 1934 was that of sending his neutrons crashing into uranium atoms. Rutherford had no way of telling, and neither had Fermi, that this, finally, was the route to the unimaginable. End of section 4. Recording by Blaine Aidan McCoy, Riverside, California, January 2019.